Welcome to the Shape of Space Linear Algebra. This is the last lesson in the Linear Algebra series, but I'll have additional series on other topics after this. This particular lesson is on multilinear transformations, which we've seen before, but we're going to go into a little bit more detail here, and also something called a dual space of a vector space. So let's start off a little bit simpler than a multilinear transformation. Let's just look at a bilinear map or bilinear transformation, which I define here on this page. The concept of a bilinear map will arise when we discuss the Kronecker product of matrices. So that'll be in another series of lectures. And the second derivatives in matrix calculus, which is yet a third series of videos that I'm going to put together. Let V, W, X be vector spaces over the real numbers. A bilinear map is a function, B, from V cross W, in other words, the Cartesian product of V and W, to X, such that the following conditions hold true. For each fixed W, so fixing one of the two vector spaces, the map B sub W from V to X defined by this expression here. So in other words, this is a constant and you're just varying over the V component. Then it has this property of a linear transformation. In other words, B sub W of A V sub 1 plus B V sub 2 comma W can be written out as in this form here. So you notice the linear transformation, the linearity is just over the V variable, and then you could just flip that and fix a V and have a mapping of basically W to X, and then that has to have the linearity property. So you have a linear combination here in the second argument, and then it divides up this way here. Okay, so that's a bilinear map. Then a multilinear map, which I'll get to on the next slide, you just have more vectors here, and you take linearity one component, one vector space at a time, and it looks just like this, except you have n of these conditions, which we normally kind of combine into one condition and just say for I equals 1 to n, but we'll get to that in a second. We have a few more slides before we get to multilinear transformations. The theorem on this slide says for an n-dimensional vector space V, a bilinear form B from the Cartesian product V with itself to R can be represented by a matrix A relative to a given basis of V, B1, B2 up to Bn, where the ij component of A is B evaluated at these two basis elements, B sub I, B sub j. In particular, for U and V in vector space V, we have that the bilinear transformation evaluated at UV is the transpose of U, which is a row vector, times A times V, which is a column vector. We first write U and V in terms of the bases, which I have here. Then we evaluate B at UV, plug in the two summations. We apply the linearity property to the first term here, and we get this. You notice the UI comes out. And then we apply the linearity property to the second, and the summation comes out, and you have this here. And since we defined Aij to be this here, B of Bi comma Bj, we can substitute that in. And then this double sum over these indices is actually the same as U transpose AV. Okay, you may need to think a little bit about why these two are equivalent. What you may want to do is just take n equals 2 and kind of work through the details. But you'll see this a lot in the future lectures I'm going to do on matrices and matrix calculus. You prefer, or we prefer, to work in this format where you're just talking about matrices and vector multiplication rather than the details of the summation, if you can avoid it. And we'll see that this actually comes up in a number of places in some future video series that I'm going to be doing. We have a few comments related to the theorem on the previous slide. As we saw, the matrix A compactly encodes the bilinear form B by storing B of B sub I, B sub j in its entries, where these B's are the basis for our vector space V. The formula B u V equals U transpose A V allows us to compute B efficiently using matrix operations. And we'll see an example of that on the next slide. While the matrix A depends on the choice of basis, the bilinear form itself is an intrinsic object which is independent of basis. But we'll see that also on the example, the next slide. For a fixed basis of the vector space, V, the matrix A is unique. A bilinear form can be represented by different matrices and different bases, but they are related by A prime equals B transpose A prime, P times P, where P is a change of basis matrix for our vector space V. And then if B of UV equals B of VU for all U and V in the vector space V, then B is said to be a symmetric bilinear transformation, and the associated matrix A is also symmetric. On this slide, we have an example of a bilinear form. It's from the Cartesian product of R2 with R2 to the real numbers. And it's defined by this expression here, where U and V are two-dimensional vectors. And you notice here we did not need to talk about a basis yet for R2. I mean, we'll need it when we compute A, but we didn't need it to define this here. So this is the example I meant in terms of defining the bilinear transformation independent of the basis. Now, if we want to get our matrix A, we do need a basis, and we're going to use the standard basis. So we need to compute B of E1, 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 E2, and so forth, the four possibilities. Remember that E1 is just 1, 0, and E2 is 0, 1. So I'll give you the details of the first one here. So if we use E1 and E1, then you're going to have 1, 1, and a 2. And then the second one is going to be 3 times 1 times 0. Then 4 times 0 times 1. And then 5 times 0 times 0. So these other three terms drop out, and you just get a 2. I'll leave it to you to do the other computations. It's pretty easy. You're only going to get one non-zero term in each case. And then we plug this into A. We get this matrix here. And that's really our final solution. But let's check to show that this expression U transpose AV actually results in this same transformation that's defined at the beginning. So we put in U as a row vector, then A times V as a column vector. We multiply this, and we get another row vector here, 1 by 2 vector, and then that's times the column vector here. Multiply that out, we get this. Then we just multiply V1 on this side and V2 on this side, and we get this, and it is the same as what we started with. We can extend the concept of a bilinear map, and we talked about this before, but I want to get into more detail here. A multilinear map is a function of several variables that is linear separately in each variable. More precisely, a multilinear map is a function f with codomain the Cartesian product of n vector spaces, and they can be different, to a vector space W, where The function f is linear in each vector space v sub I, where we hold the other vector spaces constant, just the way we did with the bilinear map, but there we only had to hold one constant and let the other vector space vary. And bilinear maps are a special case of multilinear maps. Let v sub I be of dimension d sub I, and let w be of dimension d. Let this set be a basis for v sub I. So the first element here in the subscript stands for the vector space, and the second element is just counting the different basis vectors. So v sub I has d sub I basis vectors, and that's why you go from 1 to up to d sub I. And then b1, b2 up to b sub d is a basis for w, since w is of dimension d. And then what we do is evaluate the function f at all combinations of taking one basis element from v1, one basis element from v2, one basis element from v sub n. That's what this expression is here. You notice the first subscript is from the indicates the vector space, and then this is the second one is which basis element you select. So that could be from j sub I between 1 and d sub I. And then we write the output in terms of a basis for w. So you have d terms because w has d basis elements. And then these are just the coefficients, which has a rather complicated superscripting. The superscript stands for the corresponding basis element in w, and then the subscript stands for the selection of basis vectors you've taken from these n vector spaces. Okay, so you may need to stare at this a bit to absorb it. And then this summation is just shorthand for what we have here. The above expression represents every possible combination of basis vectors, which I mentioned that. The associated mapping to w. Okay, so this is just restating what I just said here. The scalars, this set where you vary over the k and the different selection of the basis vectors, completely determine the multilinear map F. So this is similar to what we did for the bilinear maps. We only had two vector spaces in that case, and our expression here was just the matrix. This is actually an n-dimensional entity. It's you can think of it as an n-dimensional matrix. And then just one warning, I already kind of explained it, but I'll say it again. The superscripts on the scalars at the end subscripts are indices and not powers or some other indication. These are just indices, as I explained before. If we take V with components v1, v2 up to v sub n from our Cartesian product in the codomain, I want to give a formula for f of v, where f is the multilinear transformation that we've been talking about on the previous slide. So I've copied a few things down here. This was the notation for a basis of v sub I, and I'm going to write each one of the vectors in this expression here in terms of its basis. So this is the expression here. It's v sub I goes from 1 to n. It's the sum from j equals 1 to d sub I. And then we're using the basis for the ith term in here. So you notice the first index is the corresponds to v sub I. And then the j just enumerates each one of these different basis elements. And then we needed to use a double subscript for the coefficients. So the first subscript it corresponds to the placement in the vector here, v sub I. And this is also a vector, so this is a vector, those vectors inside of it. And then the j is the corresponds to which one of these basis elements. Okay, so we've taken v and we've written each component vector in terms of the basis for v sub I. Now what we want to find is what is f of v, or formula for that, where f is a multilinear transformation. So f of v is f of this thing here. And then we just plug in these expressions, these summations for each v. So we have v1, you notice there's a 1 here and here, and then we sum over to j from 1 to d sub 1. And we continue all the way up to the nth term. That's this summation here. So this is just plugging in. And then the next step is the linearity property for a multilinear transformation. So we can write this is this. Right? We've already seen that type of computation on the previous slide. So all the summations come out here. This dot 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 just means there's n summations. Then we have f of these vectors, these basis vectors, and then these are just coefficients. Okay, and then we're almost done. The last step, and I copied this from the previous slide, we computed f for a selection of basis vectors, one from each of the vectors in the codomain, and that was this expression here. We'll just use the shorthand, the summation. We plug that in for f, and then we have it. Okay, so f of v can be written in terms of the these coefficients from this equation we computed in the previous slide, as well as the coefficients for expressing the vector v. Okay, so rather a complicated formula, but you may want to spend some time making sure you understand all the steps in this. Changing the topic a little bit, I want to talk about dual spaces for the rest of this lesson. So let's first define what it is. Let V be a vector space over a field F. And as you know, we've been normally talking about the real numbers, sometimes the complex numbers. The dual space of V, denoted V star, and there's different notations, but I'll use V star, is the set of all linear transformations from V to the field over which the vector space is defined. The dual space V star is itself a vector space over F when equipped with addition and scalar multiplications satisfying the following condition. So alpha F plus beta G of X equals alpha of times f of x plus beta times g of x for every f and g in f star. So in other words, these are linear transformations. X and v, that's our vector space, and then alpha and beta are the scalars. Okay, so it's basically a linearity property that defines addition and scalar multiplication. And then we have a definition here that it's pretty simple, but I need to use this in some of the proofs that are following after this slide. So it's called the Kronecker delta function. There's different ways of writing it. I'm writing it this way here, delta ij. This is not a power. These are just indices. Sometimes you'll see it as delta with ij, both as subscripts. And if I does not equal j, then the value of this function is 0. And if I equals j, the value of the function is 1. Okay, so it's a binary function. We have a theorem concerning a vector space V and its dual V star. If we have a basis for a vector space V, then there exists a basis for the dual space such that theta sub I of S sub j equals the Kronecker delta ij. So if I equals j, then the output would be a 1. Otherwise, the output is a 0. So it's kind of an easy relationship between these two bases, and it always exists. We're going to prove that in this theorem. So the first part is define what these are, and then we'll show that they're linear transformations, and then we'll need to show that they're a basis, and that is showing both they're independent, that these vectors are independent, and that they span the dual space. So we have basically 4 parts: define these basis vectors, show their linear transformations, and then show they're a basis, both showing the independence and spanning. Okay, so let's do that. Define the linear transformations, theta sub I, so that when you apply it to a vector from V, written in terms of the basis for V, you just pick off the ith coefficient for theta sub I. And that fulfills this requirement here. You can double check, but I assure you it fulfills that requirement. Let's show, even though these are functions, we need to show their linear transformation. So we take u and v from V, write u and v as a linear combination of the basis vectors for V, which I've done here. And then we just note that theta sub I of u equals alpha sub I, that's from the definition here, and theta sub I of v equals beta sub I. Then we'll take a linear combination, shown here, multiply it out, and then collect the coefficients for each one of the basis vectors, which I've done here. Okay, and then we apply theta sub I to the linear combination. And then looking at this expression here, theta sub I would pick off the ith coefficient, which would be gamma times alpha sub I plus lambda times beta sub I. That's from this. But then we have that this alpha sub I equals this, beta sub I equals this, and we have this here. And that's the linearity property. So in other words, theta sub I is a linear transformation, and it's in the and therefore in the dual space of V. Now we have 2 more parts. We need to show these vectors, which are functions, or actually linear transformation now. We've proven that they are independent. So we take a linear combination and set it equal to 0. But this is the 0 function. It maps every vector from V to the 0 vector. That's why I put it in bold here, just to emphasize that it's the 0 function. Okay, and then we have, if we apply this function to S sub I, on the one hand, since we know it's the 0 function, its output is the 0 vector. And on the other hand, we know that applying this to S sub I, looking at these terms here, the only one that's not 0 is theta sub I applied to this, which would give you a 1, and that would be times the lambda sub I. So we have this expression here. Now remember that S sub I is a basis vector, so it's not 0. And that forces us to conclude that lambda sub I equals 0 for I equals 1 to n. In other words, all the coefficients here are 0, which implies that the theta sub 1 to up to n are linearly independent. Okay, finally we need to show that these vectors are a spanning set. so that any member of V star, which we'll call F, can be represented as a linear combination of these vectors. So we'll take any F from the dual space, take any vector U from V, write it in terms of the basis for V, apply F to U, plug this in. Then since F is a member of the dual space, it's the linear transformation. So we have this. And then we're just plugging in these equalities here. In other words, if you take theta sub 1 of U, you're just going to get alpha sub 1 and so forth, all the way down to theta sub n of U equals alpha sub n. So this equals this. And keeping in mind that the thetas are linear transformations, we prove that here, and these f of s sub 1, f of s sub n, so forth, these are just constants. So this is equal to this here, as applied to u. So we've basically shown that the function f can be written as a linear combination of the thetas in here, with again these f of s sub 1, f of s sub 2 are just constants. So we've shown that f can be written as a linear combination of these vectors. In other words, the set of thetas here is a spanning set. And thus, between these two properties here, we know that the set of thetas is a basis for the dual space. Okay, so rather long theorem, but it's useful. We'll make use of it in a number of places in this lesson and in some of the subsequent series that I'm going to be developing. It follows from the previous theorem that if V is finite dimensional, then the dimension of V equals the dimension of its dual space. That's because we showed that the number of basis vectors were the same for both V and the dual of V. We have another result. The dual of the dual, written this way or this way here, is isomorphic to the original vector space V. So I have a sketch of a proof here. If V is finite dimensional, there is a natural isomorphism, we'll call it phi, from V to the dual of V, or V star star, such that phi of V equals this entity V star star, where V star star is a mapping from the dual of V to F, where F is a field over which our vector space is defined. It's normally the real numbers, at least in our discussions. And V star star of F is defined to be F of V for F, an element of the dual space of V. Since the dimensions of V and V star star are the same by theorem 66, it's sufficient to show that the natural map phi is injective in order to conclude that it's an isomorphism. We also need to show it's linear, and that's the part I left out. I'll leave that as an exercise, but we'll do the injective part. So suppose phi of V equals 0. This means V star star equals 0, right? This here, so which implies that V star star of F equals 0, just using this definition here, for every F an element of the dual of V. And by the definition of V star star, this implies F of V equals 0 for all F in the dual of V. And the only vector V in vector space V satisfying F of V equals 0 for all F in V star is V equals 0. This is a standard result from linear algebra. It relies on the fact if V doesn't equal 0, we can construct a linear transformation F such that F of V does not equal 0. The conclusion is the null space of phi is just the 0, And then by theorem 37, V is injective. And I just have an example of this function up here, maybe to help clarify things a little. So if V is R, the real numbers, and we take a function f of V equals 3V, and V equals 1/3, then this entity here of V star star would be 1/3 star star of f, then it would equal f of V, so f of 1/3, and that would equal 3. Okay, so I have a few more theorems before we conclude this lesson, so let's go on to the next one. If V sub I equals 1 to n, is a basis for the vector space V, and phi sub I equals 1 to n is a basis for the dual of V, such that phi sub I of V sub j equals the Kronecker delta, then f, an element of the dual space, can be represented in this format here. It's summation f evaluated over the basis and then applied to the phi sub I. So any function in the dual space can be represented as this sum of product of functions. So to see this, we evaluate the right-hand side of the above at a basis vector v sub j. So we have this here, then we evaluate this at v sub j. Then we have this here, so this is f of v sub I times delta, the delta, Kronecker delta ij. And then you're going to get 0 other than the case where I equals j. So when I equals j, you get f of v sub j here. This is just 1 in that case. And so since the right-hand and left-hand sides of the above equation agree on each of the basis vectors, we just did it for any v sub j out of the set here, then they agree over all of v. So we've shown the result. The following theorem relates change of basis for a vector space V to the change of basis for a vector space V star, in other words, the dual of V. So we have V sub I and W sub I. These are basis for vector space V, and then phi sub i's and the sigma sub i's are basis for the dual of V. Assume the bases are selected such that phi sub I of V sub j is the Kronecker delta ij, and sigma sub I of W sub j is the Kronecker delta ij. We know that's possible from theorem 66. And then the theorem says if P is the change of basis matrix from the basis V sub i's to W sub i's, then P inverse transpose is the change of basis matrix from the phi sub i's to the sigma sub i's. We'll prove that in the next couple of slides. On this slide, I have some notation and some clarifications. The first line here is just giving names to the different sets of basis elements. Script S for the V sub i's, script T for the W sub i's, and so on, alpha and beta for the other two bases for the dual space. To be clear, the matrix P mentioned in the theorem is defined by W sub j equals the summation from I equals 1 to n of P sub ij times Vi. The above implies that column J of P contains the coefficients of W sub j in terms of the basis script T. Using the terminology that we discussed earlier, this is on the lesson concerning the representation of homomorphisms, P is actually the representation of the identity homomorphism from T to S. Okay, so it's kind of in reverse of what I said in the theorem, but I prefer the wording that I have in the theorem, and I just put it out here in case there's some any confusion. Then we seek the matrix Q such that sigma sub j equals the sum from I equals 1 to n of Q sub ij of phi sub I. The above implies that column J of Q contains the coefficients of sigma sub j in terms of the basis script A, using the terminology that we discussed, as I mentioned over here on this point. Q is actually the representation of the identity homomorphism from B to A. Okay, so with this in mind, let's prove the theorem on the next slide. We're finally ready to prove the theorem. The first step is to take sigma sub j of W sub k. We'll use these two formulas here. So we want to take sigma sub j of this, except we'll put in a k here for the j. And so that gets plugged in here. And then going from here to here is from the linearity of dual vectors. So the summation comes out here. We have this. And then since phi sub I of v sub L is equal to the Kronecker delta function, that means that this thing here is 1 if and only if I is equal, or L I should say is equal to I. So when this L is equal to I, this is 1. All the other terms drop out to 0, so we get a PIK here. So we get this. And then this is equivalent to I equals Q transpose P. You may need to think through that a little bit here. This is the summation notation for this product here. What you might want to do is take a 2x2 matrices, Q and P, and multiply them together, and you'll see that it's, and take the transpose first of Q, and then multiply together, and you'll see it equals this summation. Then this side here is equivalent to the identity. You notice here J and K are free variables on both sides. So this equals 1 if only when J equals K and 0 otherwise. So that's why we have the identity here. And then from here, we're almost done. We multiply both sides by P inverse. We get this. And then we take the transpose on both sides. And we get Q equals the transpose of P inverse. Okay, so that's what we set out to prove. That's the last slide in this lesson and the last lesson in this series. I'm going to put out another series on matrices, but it won't be on basic matrices like addition and multiplication. It's going to be on various matrix and vector functions that you need for matrix calculus, which I'll do in yet another series of lectures after the matrix series of lectures. Okay, so if you like this, please give it a thumbs up and subscribe, and stay tuned for a lot more videos.